On this lesson, we will start defining sequence by examination. So we'll be examining the behavior of the sequence, and then we're going to be writing down functions that will define that sequence. So let's get started. Let's start by looking at this introduction question, which says, how many terms does the following sequence seems to have? Well, first, let's identify what kind of sequence this is. This is definitely not a finite sequence, because notice that at the end we have dot, dot, dot. So this is just implying that there are a lot of terms that are going to happen after the value of 7. So since this is an infinite sequence, therefore we have infinite terms. All right, so let's start by looking at the actual objective for today, which is the idea of defining sequence by examination. So what do we mean by that? So here, notice that we have a sequence, 1, 3, 5, 7, which is, I believe it is the same sequence as the introduction. And our objective is to write down an explicit formula that we can use to define this sequence. And the way that we're going to do this is by, well, our objective is to write down expressions for the n term. And in addition, we want to create a table of values, and then we're going to use the table of values to graph the sequence explicitly. We're going to place the terms, and then at the end, we're going to see if our conclusion actually matches the sequence. So let's examine the behavior of this function, of this sequence. And the way that we're going to do this is by creating a table of values, which in this case, we're going to use a table of values for an and n, which we're just going to create a table of values for the term number and the value of the term. So n is just the value that we use to define the term, and an is the nth term. So when my value is 1, which is saying what's going to happen at my first term, well, my first term has a value of 1. So therefore, I can just define this value as 1, 1. When n is 2, I'm looking at the second term, and the value of the second term is 3. When n is 3, I'm looking at the third term, and the value of the third term is 5. When n is 4, I'm looking at the fourth term, and the value of the fourth term is 7. So I guess we don't need all this, because this should be enough. Now, let's try to plot these terms in our grid. So the way that we're going to be plotting, our x-axis is going to become the value of n, or the nth axis. And my y-axis are going to be the actual values of the terms. So therefore, we can start plugging the values that we got on our table. So let's start plugging some values. So here we have a value at the value 1 comma 1. So let's just plug that in. So here we have a value of 1 comma 1. Then at this column represents a value at the coordinate point 2 comma 3. So when n is 2, my value is 1, 2, 3. So here we have another point. Here we have another coordinate point at 3 comma 5. So let's just plug that in there. So 1, 2, 3, 1, 2, 3, 4, 5. So about here. And lastly, our last row, it indicates, column, it indicates a value at 4 comma 7. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. Now, if I take a look at the behavior of these points, these points, they kind of behave in a linear form. Because notice if I connect those values, okay, that's a very bad connection. All right, so there's a better graph. So notice if I connect the value of my sequence, the terms behave like a linear function. So perhaps I can come up with a function or a formula for the sequence in a linear form. So perhaps if I know that my sequences are behaving in a line, so perhaps I can define perhaps I can define my terms in a using a linear function. And if I want to define a linear function, all I need is just the slope and the y-intercept. And to define the slope of this line, I can kind of see that the slope is rise over run. So it seems like I'm going to go 2 up and 1 to the right. So here I can see that the value of my slope is just 2. And the y-intercept, well, I can use my slope to define my y-intercept. So looking at the value 1, 1, I can go 1, 2 down and 1 to the right. So I can see that my y-intercept is going to be at the value 0, comma, negative 1. So now I know that might be equals to negative 1. So now, noticing that my sequences behave in a way of a line, in order for me to define this line, I know that my slope is 2 and my y-intercept is negative 1. So now we can use that to define a formula for my sequence. Because now I can say, look, my sequence or the value of my sequence can be seen as 2 times n minus 1. And notice that this follows the y equals mx form. Because here this x is my x-axis, which notice that here my x-axis is n, and here my y referred to as the value of the y-axis, which the y-axis is a of n. So here, notice that it's essentially, we just graph a line, we examine that line, and now we use that idea to define the sequence for this, formula, explicit formula, I should say. Notice that we're using an explicit formula to define the sequence now. So therefore, if I want to find the 100 term now, I have a formula that I can use. And we were able to define this formula just by examining the behavior of the terms that we know about this sequence. And this is what I refer to as defining sequences by examination. So here we graph the sequence, we graph the terms, we look at the behavior of those terms, and then we use that behavior to define an explicit formula, which we can use later to define terms in the sequence. Let's do one more example. Let's do example C now, which I don't know what happened to B, but let's just take a look at C then. Same idea. We want to come up with an explicit formula which we can use to define this sequence. Well, the first thing that I want to do is, well, let me create my table of values. So here we have a table value for n and a of n. Same idea. I'm going to start with n being 1. So the value at my first term is of 2. The value of my second term is of 5. The value of my third term is of 10. And the value of my fourth term is of 17. And I guess we don't need this. So let me just scratch it off. Same idea, our x-axis is going to become our n-axis, and my y-axis is my a's of n. And notice that here I want to try to plot a point of 1, 2. From here, this refers to the point of 2, 5. This column refers to the value of 3, 10. This column refers to the value of 4, 17. So therefore, let me just plot those values here. I'll be back in a second. So now that we have plot those values, notice that the first thing that I can notice is that this is definitely not a straight line. So this sequence doesn't behave just like our first example. Our first example or sequence behave in a line. So therefore, I was able to define my explicit formula as a line. But by looking at the way that these points are behaving, you can see that this is not a line. You can kind of see that this is some kind of a parabola. But notice that here we have this curvature going on. Notice that here we have some kind of a curvature going on. So perhaps the way that these points are behaving is they're behaving like a parabola. But now let's think about how we're going to define this parabola. It kind of seems like it's a parabola whose line of reflection it's on the x-axis. So this is a parabola whose line of reflection it's on the x-axis. So let me get a point and let me reflect it over the y-axis, which in this case the a-nth axis. So if I get that, I want to get a point and let me reflect it over the y-axis, which is about right here, which is we're 2 units away from here. So here about 2 units away from here, And again, I'm just guesstimating here because this is just by examination. Like we just want to see a pattern. It seems like we have some kind of a parabola that will behave this way. Well, this seems to be a parabola. This seems to be a parabola, which is just shifted 1 unit up. Therefore, perhaps this parabola can be modeled just using the expression x squared plus 1. So perhaps the way that we can define my sequence is a of n. Perhaps I can define it as n squared plus 1. This seems to be a very good guess because by looking at the way that my initial points were behaving, I can kind of see that it was a parabola. And it seems to be a parabola that I just shifted 1 unit up. So therefore, I can perhaps define my sequence using this formula. And now, I guess one thing that I forgot to do on the previous example is that whenever you have defined a sequence using explicit formula, let's just verify to see if the points actually match. So what happens when we plug in 1 to our explicit formula that we obtain by observation? Well, if we plug in 1, we're going to get 1 squared plus 1, which is 2. And that's exactly the value of the first term. So what happens if I plug in 2 to my formula? So 2 squared, that's 4, plus 1, that's 5. So it seems to start matching up. So what happens when n is 3? 3 squared, which is 9, plus 1, that's 10. 4, 4 squared, plus 1, that's definitely 17. So notice that this seems to be the explicit formula that we were looking at. It seems to be like the explicit formula that we can use to define the sequence. It's defined as just n squared plus 1. And notice that the way that we obtained this formula, it was to first just pull up the points and see, well, is it a line? Is it a parabola? What kind of a function does it seem to be? And then use that idea and just start estimating some functions. And then at the end, your job is to verify that that explicit formula matches up with the values that we got initially on our table. And I guess you definitely want to verify, so let's just verify the formula that we got on the first example to see if it actually is 2n minus 1. So what happens when we plug in n equals to 1? So we got 2 times 1, which is 2 minus 1, which is 1, which works. What happens when n is 2? 2 times 2, that's 4, minus 1, that's 3, which is the value that we got here. What happens when n is 3? 3 times 2, that's 6, minus 1, which is 5, so it works out. And what happens when n is 4? 4 times 1, that's 8, minus 1, that's 7, so it works out. So notice that we were able to define explicit formulas for those sequences by just observing the behavior of my functions or the behavior of the terms in the sequence.